Okay, welcome to this lecture of the GeoDatabase course. I hope you all managed last Wednesday to do the spatial indexing and see the difference. Yeah, one remark about the lab assignments. If you have questions, it is best to ask the persons involved. That could be Marianne de Vries or Wilco Kwak. Because they are most deep in the lab assignments. Of course, I'm always happy to try, but it's better to ask them. Okay, today's topics is mainly focused about time, and in the second part, a little bit about the land administration as an application of geomatics technology. And the first part is about time, and that knowledge will be used also in the second part in the land administration or in cadastre. Okay, last time when I did the polls, you scored very well when I did the poll before the lecture. Maybe because you did careful reading of the reading materials. So I will now start with a poll about time in GIS. And if all is going well, you should be able to see the poll about time in GIS. And yeah, please think about these two questions. And so if you are developing a database or an information model that has to support changes over time, and then you want to go back to a certain moment in time, what would be the best model? State-based model, event-based model? And the second question is, okay, what are the key aspects of the space-time theme triangle? And I see the votes coming in. I will wait a few more seconds until at least, say, 15 votes have arrived. And I know I did not cover this in the lecture. It will be covered. So maybe the questions are difficult or hard now. If you did the reading, it may be easier. Also, test on the reading and your memory of that reading. Okay, I will count down and then I will stop the poll. 3, 2, 1. Stop now. And I will share the results. Okay, the first question, the majority of the answers is event-based modeling. And actually, that is not correct. The state-based modeling is easier to go back in time, and during the lecture, the first part, I will try to explain this in a clear manner. The second question, I see a lot of different answers. All options do have a score. And I hope you can also see these scores. But the highest score is ID, space, scale, and time. And that is indeed the correct answer. But the others also got quite a good number of votes. But in the lecture, I will explain this triangle. Okay, I will stop the poll now. And I will start sharing the screen. I will do the whole screen first and then go to the proper PowerPoint. Okay, in your education until now, the focus was on the geometry aspect of information, geographic information, and that is very clear because we in geomatics worry a lot about the geometries. in observation, in measurements, in representations. But I will try to make clear in this lecture that also the temporal aspect is really important. And actually, it is the temporal and the spatial components together that makes a modern GIS work well. So that is what is covered first. Then are some theoretic principles about temporal modeling, some system or implementation aspects related to modeling of temporal information, focus on modeling parent-child relationships in time. Then already going a little bit into the cadastral domain or land administration domain, I will explain the model of the Netherlands cadastre, the information model, and how it's stored in a database table, and how time is there being used to register the updates, and how that can be used in applications. For example, deliver update files to customers and use it in visualization. Another application of time is topographic application, where there are different owners of the topographic map, and one is maintaining, but you should also pay for the maintenance. And a fair way of doing that is by looking at the number of changes in a certain area and in a certain time interval. Okay, one of the very first researchers that was looking into the temporal dimension in relation to geographic information systems was Legrand, and she did write a PhD thesis about this topic. And here you see a number of questions and why time is important in geographic information applications. For example, where and when did something occur? What was the type of change? What was the rate of change? Is there a trend? Is there a repetition? If so, at what rate? You can ask questions also about the history. Where was this object 2 years ago? How did this area change over the last 5 years? And perhaps one of the most difficult questions is try to figure out what processes underlie these changes. So you can explain the changes and perhaps even predict the future. And this was a kind of categorization of the different temporal values in the GIS. So it could be used as an inventory, count at a certain moment, count the parked cars on the roads. It could be used for analysis, so seeing changes, for example, in water level, and trying to explain that, or in temperature, or in population of a city. And you can have many different types of themes or phenomena. Time is, of course, also needed when you are doing updates. So, when something in the reality changes, you must also update your map. And you can then update and keep the history. Quality control. Okay, things cannot change instantly, at least not physical entities. So if you have a certain elevation model with sand dunes, for example, and on 1 week you have an elevation of 14 meters, then the next week the same sand dune could not be down to 5 meters. If you measure that, probably something is wrong with your measurement or your earlier measurement, or something else happens. But it is at least a tool to do some consistency checking between the old and the new data. You can use it for scheduling. So if the things do change over time, that at certain thresholds, at certain moments in time, you can trigger an action. For example, if you measure the water height, then at certain moments in the Netherlands, we lock off the sea by closing doors, locks to the sea. But this could also be in very different context. If you monitor the state, and then if you reach a certain state, you take an action. And also very interesting and important for the understanding is visualize the temporal dimension or the changes over time. And then as a human, you start to understand what is happening out there. Okay, this is why time is so important in geographic information. And I think until now, you will not have done a lot with this aspect, at least not explicit. So some of the conceptual foundations, there are different changes over time. Is it a discrete change happening suddenly, or is it a kind of gradual or continuous change? For example, a discrete change, like if you split your parcel and you sell a part, and that happens at one moment. There is one moment where you transfer the ownership of that new part to the new owner, and that is not a gradual process that the part of the new owner is growing and growing. No, at one moment in time, the new parcel is created after a split of the old parcel, and that fits very well in the vector model. So you could say for these man-made kind of things, the vector or object representation is very well suited. For continuous changing things, like the elevation of the sand dune or the temperature out there, the raster model or the grid model is a good representation, and the sampling nature. And normally a grid is, say, a spatial grid with X and Y dimension or rows and columns. But also you could consider the temporal dimension, and then you get, say, a 3D grid. And that fits very well to describing many natural phenomena. And especially also the process modeling, erosion and depletions, that fits well in the continuous representation of the raster or field model. An example of such a continuous change is what is happening at the Dutch coast. There we have the dunes that protect the Netherlands from being flooded. We are always worried about that because due to erosion by the sea, we lose sand. And there was one big project started a couple of years ago called the sand engine in Dutch zandmotor, and incredible quantity of sand was depleted outwards in the sea to form also some dunes in the sea, and to see if that would change the overall erosion of the whole coast in that area. And therefore Rijkswaterstaat is monitoring that part of the coast on a daily basis by new scans, by laser scanning. Perhaps you remember from the sensing technology course that you can get very detailed observations by laser altimetry. And so, and also a lot of points. This data set, the spatial temporal data set, was used in the thesis by geometric students, how to organize the spatial temporal data, how to do queries, and how to visualize the changes. Okay, this is a triangle that tries to depict at a higher level conceptual modeling of information. And if you think of it in object-oriented modeling, what you did with UML class diagrams, creating classes, per definition, an object always gets an ID. And so that is put in the center here. So that makes an object exist. If you have an ID, you do exist as an object of a certain type. And then you have descriptions. And for us, we always focus on the spatial descriptions, the geometries. That can be in 2D, can be in 3D. So on the plane or in 3D space. We quite often attach thematic aspects, either in the classification, that you are a road, or you are a forest, or you are a lake as an object, but sometimes also in multiple attributes that describe properties of the object. For example, the type of the tree or the age of the tree. The age is perhaps not a good example because it is going to the third corner of this triangle, and that is the temporal dimension of a model. And so the tree is planted on a certain date and is still living, or perhaps maybe cut down or died. You don't know, but if you want to register that, you have to have an information model that allows you to include that in the model. This time aspect. And if we put together the space and the time and integrate that in a higher dimensional representation, than 2D space and time. If we look time as one dimensional, we get a 3D representation. And if we combine 3D space and time, we would get it 4D representations, which are very hard to imagine. I cannot imagine them, but you can think about it. And this is an example of time as dimension. We have the normal X and Y coordinates. On the bottom of this cube, you see here a map. And on top of that map in the third dimension, that is the time dimension, the T, you see all kinds of lines moving. And these lines are moving up because you can only move upwards in time, but they are also moving in the horizontal direction, X and Y direction. These are paths of birds that were flying above the Netherlands, and these birds were tracked with a GNSS device to determine their position. And so they moved around in the 2D or the 3D space, but it was projected on the 2D location, and the time dimension is used to see, okay, how fast they were going. So if you're going steep, you're going fast. If you're going slow, no, completely wrong. If you are steep, you're going slow, and the most slow is if you are standing still, because then you will be pure vertical. If you are going near horizontal, then you are going very fast. So the steeper you are, the slower you're going. So you can try to make this kind of interpretations, and you can move around in the cube. You can rotate it. And this example is about a certain pollution above the Netherlands that we try to not show in 3D space, but in 2D plus time, where the third dimension is now indication of how severe the pollution was at what location. Okay, this is an invention of a geographer already half a century ago, Hagerstedt, and this is called the space-time cube, this type of representation, integrating space-time. Okay, so more basic concepts. The smallest time unit is called chronos. I have depicted here the timeline, and time is a bit different than in space, because time is also kind of always moving forward from the history to the future. There's one specific point on the timeline that is now, but what is also strange that now is never the same. Now is always moving forward. That is different than the location. I'm now sitting on this position. It's not changing, so XY is not changing, but time is changing. And that is a bit like this bird was sitting on the same location. So the XY is the same, but the Y is always changing. And the time or the time dimension is always changing. Instead of a moment in time, we can also talk about time interval. Then we indicate a start and an end on the timeline. And we can have frequency of patterns that reoccur. For example, the working hours or the studying hours in the week. So every week you more or less have the same pattern for a certain time of your study. So that is the frequency of an event. Okay, we talked about topology of spatial objects. You can also talk about topology of temporal objects. And if you consider moments in time or temporal points, you only have three options. Either the points are equal, so same moments, or one is before the other, or one is after the other. And you could say before and after are reversing the role of the operands. With intervals, it gets a bit more interesting. The two time intervals can be disjoint. So these two objects never live at the same moment in history. These two objects touch. That means exactly at the moment when these objects start to end, the new object starts to live. Overlap, they exist together for a while. Include, the life of one is completely covered or contained in the life of the other. And here the life is by coincidence or not coincidence of two objects is exactly having the same span. The simple topology and timeline is in reality perhaps a bit more tricky if you consider alternatives for the future or different design proposals for changes. Okay, we have one history. And in the future, we may have a proposal number 1 and a proposal number 2 and a proposal number 3 with two options here in the end. And we may want to represent that in the database, in the information model. So the topology is, in such case, a bit more complicated. I talked about time as if it is just one thing, but when we are storing time in the database, we have to think, okay, which time? When it happened in the real world, or when we observed it, for example, the aerial photo was taken, or when it was stored in the database, or when it was last checked in reality, or when it was made official by a signature, for example, a transaction. Or in some cases, we may also discover an error in the recording, and we would like to correct the past. And we would even like to correct it in the past. But okay, we can only correct it now. But okay, somehow, if you have to pay, for example, taxes over a certain time interval, then it's important that also the past is corrected. Otherwise, you would pay tax or wrong tax, because The tax is based on the whole year. Or if they discover pollution in a certain area, it's important to know who is the owner. And also, if we would have then the wrong owner and not the corrected owner in the past, then the wrong person would be held responsible for the pollution. So therefore, it may be important to correct also errors in the past. But as you know, time traveling is impossible. And especially if you watch the Doctor Who television series, you know how tricky it gets. Because, for example, if you change an object and say, okay, that object has never existed or was much smaller, but say, make it extreme example, an object that was in the database was an error and it should have never existed, but it was in the database. And at a certain moment, that object, for example, think of a parcel, was split into two parcels, and then two new parcels existed, and you could call them the children of the parent parcel. They are there. And okay, after the children are there, 1 or 2 years later, it was discovered that the parent parcel was a mistake. And what happens to the children? And so you can have many related objects and references, and changing the past is dangerous. It could give a kind of time rimple. And yeah, also important is, okay, when we store data in the database, and if that data has not been used or seen, we may change it or correct it without telling anybody, just correcting it. If we know that somebody has seen and used this information, for example, the one who sent the tax invoice, then when we are correcting it, we also have to send this person that have queried the database. Sorry, you queried it some time ago, but we discovered an error. And please try to correct your action and send perhaps an update of the tax invoice. So that is why also the access to the data is an important moment in time. But okay, there are so many options. So what can we really do? I suggest we now have a short break, a 5-minute break. Then I will try to continue with the other parts of the temporal introduction. So see you back in, say, 1418. If you have questions about the first part, the principles, it's now a good moment to ask them. So open your microphone. Okay, it remains silent. So I will stop the lecture for a while and see you back at 1418. Okay, welcome back. It was not really a full 5-minute break, but there's a lot to cover in the remaining part. And yeah, please do interrupt me when something is unclear. It's really hard to make the sessions interactive, but yeah, don't hesitate to ask a question or yeah, raise your voice. Put it in the chat, and in a break I will have a look at it. Okay, we covered the motivation and the principles. Now have a look at yeah, the system aspects, or how to implement it in a database environment. We saw many moments in time, but we can also think about, okay, when we are modeling, at what granularity do we include the time in the database? And there is a kind of tradition to have a very coarse granularity, especially in the time of the paper maps. And then the whole data set got more or less the same timestamp. And yeah, every 6 years or every 4 years, the whole map was updated based on aerial photography. And after 6 years, there was a new release, and all objects were then checked and remapped again. Of course, people yeah, did not expect it or accept it anymore in the information age, and more frequent updates were yeah, required, for example, by the users of the topographic map or the base map. And especially the important classes like the roads, people use them a lot to do all kinds of tasks. And at a certain moment there was an agreement in the Netherlands that depending on the object class, there was a more frequent update. And then every 2 years, all roads would be updated. All new roads would be added, or the changed roads, or the removed roads. And so this is a little bit more detailed already, because this is the whole map and this is the whole class. And a step further in the refinement is that we do not do the whole class every 2 years, but we do changes at object instance level. For example, when something changes, we want to record it as fast as possible in the database. And that is happening with the cadastral map, when the parcels are changing because of selling and buying by people, splitting parcels and merging parcels. We want to see that directly on the cadastral map, because it's really crucial in such a map that you know who is the owner. And with the digital technology that is possible, so you could say the cadastral map is having a more fine granularity and higher update frequency. Also nowadays, if you look, for example, at OpenStreetMap, which is a kind of VGI, voluntary geographic information, people from all parts of the world contribute to it, and that really happen at instance level. One object can be added as you drive with your bike, or you walk on a new path that is not on the map, and you can upload it yourself, and then there's one new object to the OpenStreetMap. The finest level of granularity is at attribute level. For example, an object is yeah, relatively static for most attributes. For example, the name of the object and the location. For example, the shape of a river. But one attribute is changing a lot. For example, the water level could be in a river, or it could be in a groundwater measuring point. And then the object, the groundwater measuring point, is not changing its location. It's not changing the name, but every hour or every day, the groundwater level could change. And so this is the highest granularity with impact on the model. What we see most is time at the object or the record level. So that is the third level over here, this level of granularity. So when something changes to an object, and the whole object instance is updated. It's because it can be well implemented. In the implementation, there are two options, state orientation, and then for every object, you extend that description with some time attributes, usually two, tmin, tmax. And tmin is the moment when the object becomes valid, and tmax is the end of the lifespan of that object. It's invalid, not existing anymore. So that is state orientation. When you add to the table these two timestamps. And the other one is event orientation. So then you store in your model the changes, the things that happened. And with that, you have to explain, okay, which attribute did change and when did it change, perhaps why did it change? Because it was sold or because it was flooded, something changed. Depends on the object or the table. And with the event orientation, you can have a forward or a backward reasoning, but assuming that you want to maintain the current map, then with the events you can go back in time by kind of undoing an event, and then you know, okay, which attribute was changed and what was the value before the change. It could be the geometry, and then you can show that on the depiction on the map. But when it is long ago and many events have happened, you have to process a whole chain of events to go back in time. You can also do the opposite. Say, okay, I store the first map, and I store the changes afterwards. But I don't change the first representation. So if I want to have the map of now, I have to apply all changes, and then I can have a correct map. And okay, that is not so effective. Only for the historic map it's effective, but if you want to see the map of now, and that is the most used map, then you have to do a lot of work. So that is not a good option. It is forward reasoning. So here are two questions you could ask to a database with temporal support. Give me the map at moment t. That is quite often asked, and then most often t is now. And the second question that is asked quite a lot is give me all the changes in a time interval between t1 and t2. And for example, t2 could be now, but not per se. And I hope you do understand that the state orientation is best for answering the question, give me the map at moment t, because what you do is you do a query where you check if the t is within tmin and tmax. So the interval tmin, tmax does contain t. And these are the ones you have to show to give the map at moment t. And with the event orientation, you have to do the chaining either forward or backward, and that is not so efficient. So this was the question from the beginning, and the correct answer was state orientation. Before the small break, I said many moments in time are relevant. One moment which is used a lot is the system time, because that is the time the object enters the database, and that's also what you can control and can check. That is called database or database transaction time or system time. But another time that is very important is the valid time. When did it happen in the real world, or when was it valid in the real world? And if you have these two times, you need actually 4 values. And look at this timeline. This is all about one object. The user time is, okay, this object was valid from this moment to this moment, but there was a delay in capture, and actually it was then stored at this moment in time, entered in the database, and it was removed from the database or made clear that it was not actual anymore at this moment. So these form values, and these two timelines can be combined in this kind of conceptual rectangle in the 2D space. So this is a 2D time space. On one axis the system time, and on the other axis the user time. And this rectangle is a kind of the life of a object that I depicted. And this is also state-oriented with begin and end time. So the visualization, what could we visualize? The current, or at the current time, or at another time, a fixed moment at least, a snapshot. The changes in an interval. We could show it side by side on the screen. On the left side, the old map, and on the right side, the new map, and you can see the changes. You could also see the changes by an animation from the old map, step by step by step, going to the new map. And then you can decide, okay, the steps in time are these absolute steps. For example, every new map is 1 year further. Or is it you do a step when there is a change? Because if you do always a step, even if there is nothing changing for 3 years, and you look at you're looking at the same map, could be good. But you may also decide to do the other option. As Hagen said, you can show time as the third dimension in the space-scale cube kind of representation. Or you could also use cartographic symbols to mark temporal events. And you could use color or symbol size to indicate the change rate or the change type, and mark these locations with the symbol. Okay, now a bit back to Earth. What is there in the relational database? And there is a proposal to extend SQL standard with temporal support called TSQL. That is not yet very far in the acceptance, but despite the fact that the standard is not yet there, there are already quite a number of databases that gives you a good support of the temporal dimension, and they do it at object level and system time only. And for example, Infomix and Oracle has versioning of all your records, and also Postgres has it. So try this query when you are behind your laptop and open the Postgres database. Select everything from a table you already have, but then instead of just star, also add two other attributes, tmin, tmax, and you can say, okay, I never defined tmin, tmax. Correct. You do not need to define them. Postgres makes them for you automatically. But they are there, and you can select them, but you could also put them in the where clause to retrieve objects that were valid at a certain moment in time, in the past or now. You could be worried that by this tmin, tmax system, but what does tmax mean? Actually, if you delete records, they're not really deleted. They are still in the Postgres database. Only when you do a normal select without tmin, tmax, you don't get that record that is deleted. If you add this tmux in the query, you will also see that you will get deleted records. And yeah, this growing of a database, because if you have many updates, there will be a lot of historic versions, could be worrying. And therefore, there's an option to remove all historic data. In that command is called vacuum in Postgres. But in reality, the size of the data storage hard disks is often sufficient to manage the growth of data, the historic data. Okay, one thing about unique object identifiers and the relation to keys in the database. And so in the normal object-oriented modeling and also in the space-time theme triangle, the object identifier or OID plays a very important role. And in a temporal system, when you make a new version of an object from the same object, the object keeps its identifier. And so you would have multiple records with the same identifier. And to make it unique and to be able to select a specific version, you can add to the ID, to the object ID, also the tmin. And that would give you the database key in your relational model. And this is a good solution. A long time ago, I worked for the Netherlands Cadastre, and I redesigned the cadastral information system where all the parcels are stored. And we took the decision that the key was the identifier plus tmux. And I say now that this is not a optimal solution. Would anybody have a clue why I now say I have to admit this is a kind of failure? Anyone? I'll give you a few seconds to think about it. And I will take a sip of my tea. No one? The reason is, if you remember Wilco's lecture, that a key in the database should be stable. So you may not change a key value. This pair of OID and tmux is not stable. Okay, OID will not change, but tmux does change. And when you have an object which is still valid, tmux is null or not set or infinite. And when the object version is ending, tmux gets a value. So tmux is changing. And it is not good to have changing values in your key. Tmin can never change. When an object is inserted, it gets a timestamp, tmin, that will never ever change, because that is system time. So this is a better alternative. Okay, identifiers and references. So in the database we have references, primary key, foreign keys, and we refer from one object to another. And be aware that when you have a temporal database, you should not use the full key, like the combination of ID and tmin. Because if you would do that, one change would mean that you have to change all referring objects, because the references are also being updated. And I will try to explain this in detail later on. When I come to the cadastral model, so For now, remember, when you have a temporal database and you have versions of an object ID and a time to make the key unique, when you are referring to an object version from another table, only use the OID part. Otherwise, you end up in a problem. Okay, next part. I will go over this a little bit quicker. Modeling parent-child relationships. So what are these? For example, I have one line in my system, in my GIS or in my database, and I'm going to split this object into two objects. So here I have one line, here I have two lines. The geometry is the same. I kept here an object identifier, the 1023. So here you see the content of a spatial temporal table. So OID 1023, this object has three coordinates in the geometry, in the shape. It has a certain quality attribute, quality 1. It was created on 12 January. And the split happened on 20 February. This is the time of the split. I can read it from this table. And on 20 February, you can see in the next two rows in this column, I get two objects that come to exist. A new version of 1023, only with two vertices, the first part here. And I get a new version, 1268, which also two coordinates, but different coordinates over here. They both inherit the same quality. I can see that the first part is changed again on 14 April, and that the second part is not changed. It has still the max time, so that means it is still valid now. But on 14 April, something else happens. Object version 1023 got a new version, 1023, you can see it here. The geometry did not change, but one of the attributes did change. And so this whole table is capturing the whole history of this editing over time. There is a kind of parent-child relation or successor-predecessor relationship. In part, this is implicit in the object identifier. When you keep the same object identifier, example the 1023, but it is not clear for the other part, the 1268. You cannot know that that is also a kind of a child of the old object 1023. You can figure it out if you do what is here called a spatial temporal overlay. And then you can figure out, okay, on the location of 1268, which objects were lying there before. And you can say, okay, these were kind of my predecessors in time. But it's a lot of searching, doable. You could decide to explicitly store also the parent-child relationships. And here is a table with the parent and the child and the moment that it happened. So we have one parent, 1023, that has two children, 1023 new version here, started to exist at 20 February, and the same parent has another child at 1286, also starting here. And so this little table captures the parent-child relation between the objects and their versions. You can have more difficult, say, changes over time. I've now not a line, but say here 3 parcels. And after some kind of reorganization, I get 5 parcels, 2 here and 3 here. And if I then want to cover the parent-child relationship, I get a kind of table with quite a lot of combinations between the parents and the children. So I have 3 times object number 10 as parent with 3 different children, and I have 3 times object 31 also for the same 3 children as over here. The set is the same as this set. So this kind of redundancy in the table content, it's not really redundant, but okay, I don't like it. Could it be not done more elegant? So here it's this type of redundancy, repeating the same IDs of some children and some parents in different combinations. Instead of the simple table with parent-child, if we make a model like this, which is organized about, say, cluster numbers, and you could think that a cluster is a kind of an event. A cluster has a time. A cluster has a number of participating parents, 1 or more, and a cluster has 1 or more children as the result. And in this way, you could store the same information in these 3 tables. And so this is exactly the same information before, but now in 3 tables. There is still a bit of repetition, but okay, that is because in cluster number 1, there are 3 children involved, and in cluster number 1, there are 2 parents involved, and yeah, we have to record it. Okay, somehow I'm never satisfied. Somehow I think these 3 tables are a bit heavy to model. An alternative is a table like this. Same concept of the cluster of changes. So we have 2 clusters of changes with parents involved and children involved. And now I make them a bit not normalized relational. I introduce a repeating attribute value. So in one attribute, I can have multiple values. This is now possible in Postgres and in other databases. A pure or a purist in relational algebra will say, I don't like this way of modeling. But yeah, for me, I think this is the kind of the most compact and simple way to represent what happened over here in the child relationship modeling. Okay, I'm gonna go one step more in detail. I'm gonna take you to the cadastral database I redesigned when I was working in the Netherlands cadastre. Here in yellow, you see the object identifier, and this is in the table parcel. I'm now showing 1 record, and the parcel over here has 2 timestamps, tmin and tmax, 2 values, encoded as integers, and I made a kind of function to convert an integer to a normal time. Somehow I like these integers, nice and compact, but when you look at it like this, it does not tell you so much. But it is compact. So the unique key of a parcel would be the OID and tmin. I was also talking about references. Actually, the parcels do not really have their own geometry, not so much. Okay, they have a little bit of geometry, a center point. So you see the X and the Y of the center point, and they have a bounding box, but the actual boundary is somewhere else. That is another table called boundaries. And the boundary has an actual shape, which is a line or a polyline with number of coordinates. the general things are the same. So also a boundary has an object ID over here, this number, and also a boundary table has tmin and tmax attributes shown over here. And now the references. And so here is from the parcels, there is a reference to the boundary or to the lines. And here you see this number. This is referring to this record actually. It's not by coincidence I showed these two records next to each other. They're referring to it. But also there are many boundary to boundary references. These four actually, they are referred to other boundaries. And there are two references back from the boundary to the objects, to the parcels, left and right. So this is the left, and this is the right one. And if you look over here, at the right-hand side, you will see that this value 177612, and is actually on the right-hand side of the boundary, there is the parcel. Okay, here you see a picture making everything much clearer. And so I was looking at this boundary, the thick black boundary, and this yellow parcel. And here you see the numbers of the boundaries. And we implemented a type of topology that is called winged edge. And why? Because when you are looking at every edge or boundary element, it has 6 references to the areas left and right, and it has 4 references to other edges. At the beginning, so 1 to the left and 1 to the right, and at the end 1 to the left and 1 to the right. And it's nice because this number is always fixed, and no matter how complex it is, and I will try to make a bit of a different sketch. And so yeah, here you see also in this case that at the end there is 1 to the left and 1 to the right, but it could be that there will be many more points. Something funny happens ending here. And so the number of edges that meet in a node, you can never know. It can be even 100. And so that is totally unknown. But you always know if you follow these 2 references, that from 1, and then I'm at this edge, and also at this node I can go to the next one, and when I'm at this edge I can go to the next one. You can kind of circle around this node and get in the end all incident boundaries or edges. Okay, here a brief summary how this time at object level works. And so a record gets 2 timestamps, tmin, tmax, like in Postgres. And when it's inserted, the check-in time is set, and the end time is not set or put to the maximum value. So that is infinite. When you delete, it's very easy. You just set the time of tmax to the check-in time, the current time, the transaction time. When you want to do an update, that is the kind of the most complicated thing. You make a new version of the complete record, copying everything, but set tmin in the new version to the check-in time, the current time, and tmax to max int or infinite. And for the old version, is also copying all the attributes. You just set tmax to the current time, the check-in time. And these 2 times, the tmax of the new version and the tmin of the new version and the tmax of the old version should be the same value. Otherwise, we could get a gap in time, that there was no parcel at a certain location at a certain time. So with this scheme and this filling of the tmin tmax attributes, it is very easy to get answers to our two queries. Give me the map at moment t, t being now or a moment in history, or in the future if we make predictions, and give me all objects that changed in this interval t1, t2. And to prove that, I will show it in the next applications. Sending updates. The reason why the cadastre introduced time in the database while I was working was that they have customers that use cadastral maps and also topographic maps. And these customers, the municipalities, the water boards, utility companies, did not like to receive complete new copies. They just wanted to have changes. And to produce such a change, the cadastre had to compute all the differences. And so they did not have time in the database. So when they delivered an update or a copy to a customer, they put also a complete copy of the content of the cadastral database on the shelf. And when they had to do a new delivery, they compared the historic copy with the current content. And that's a lot of computation, all these differences. And the hardware company that was selling computers to cadastre was very happy because they could sell a lot of hardware. But at a certain moment, even with the additional hardware, it was not possible to finish computing the differences within 1 month of time. And that was the smallest delivery interval the cadastre was delivering the updates. And so they started 1 month ago, and by the end of the month, they could not deliver the changes. And so much computation was going on. And it was the main motivation why the time was introduced also in the storing of the cadastral database. I will now see that these updates or these change files sent to customers to update their databases can be based on either seeing the time as a whole interval or as 2 points. And the customers may receive not all attributes, and there could be changes in, say, internal attributes that are not relevant to the customer. And in such a case, you would not want to give an update to the customer because all visible attributes to the customer are the same. And so these two views on the type of delivery, interval or a point, or all attributes or only relevant attributes, that would give you 4 combinations of products. This is the only queries I will now explain in detail to produce the records that are changed. Actually, just 2 queries. So we have a table, which is called line, and abbreviated as L. I select everything, and I want to deliver the lines that are either deleted or changed or updated. And that means their end, their tmax, falls in the delivery interval, and that is from begin to end. Tbeg to tend is the delivery interval, and tmin, tmax are the times of the objects. So if the tmax of an object is in this interval, begin is smaller than tmax and end is bigger than tmax, then it is a deleted or a changed object, like in this case, or in this case, or in this case. So this is the same object with OID X, and it will be reported twice as delete or updated object. And the same object also causes a number of new versions to be reported. And you have a new version when the tmin, the start time, is in the interval of the delivery from begin to end. So that happens over here. Here is a new timeline starting, and here is a new timeline starting. And so this will be delivered. And some customers may be interested in the intermediate changes, and some others not. And I will not spend time to explain these queries to avoid skipping intermediate changes and also looking at the moments in time and not the interval. But the queries are not much harder. They are a little different. This is about attributes that change or do not change or relevantly change. A small visualization. So this is the map a long time ago. Okay, it was when I was working there. This was before a reallotment. So sometimes they reorganize the parcels, especially for the farmers. So this was before, and this was after. So look at the differences. So in generally, they try to make the parcels bigger for the farmers because then it's easier to farm. And these small parcels are there due to historic reasons. For example, a father is dying, and then the children inherit parcels, and the parcels are split in a specific way. Okay, this is better. Perhaps it still looks not like an ideal parcel to you, but it's better than the previous one. So this is one way to visualize the change. Another way is using colors. I'm not sure if you can see it well, but here there are some black lines and blue lines. And the blue lines are the ones that are going to change due to a new survey. These are the red ones. They are the new surveys. You see some blue, red on top of each other. That means, okay, some centimeter differences, but you also see here some blue where you don't see any red, and the other way around. That means something has really changed in this situation. You can also do a color coding of time. For example, the tmin time is color coded, or tmax is color coded. Another application I was involved in my cadastral time was the topographic map. So the topographic map is used by many organizations, owned by many organizations, but one is maintaining it in a certain area, usually. And then the others have to be compensated. And there was an agreement that the compensation is based on the number of changes in a region over time. And by having the history in the database, and here you see the complete topographic map, and not color, not with colors, but just the line work. And in the fat black lines, you see the changes that occurred. Some new buildings being created here, or some new road work over here. Different types of changes. So some road work over here, or perhaps a fence that has changed, or a little canal. And based on these changes, the billing was then arranged. But that was possible because the changes were recorded in the database, and we could do queries to retrieve these kind of queries. Okay, to conclude, I discussed quite in detail one temporal model, object-based, using the state representation, tmin, tmax. I don't claim this is best for all situations, especially if you would have, say, natural changing features. You probably would be using other objects. There is also some standardization ongoing, and temporal aspects are expected to be part of the future ISO and OpenJS standards. And since this year, 1997, 1997. Yeah, the Netherlands cadastre contain the changes with this temporal model as I just explained, and I'm very proud of that. It works well. Even after I left the cadastre. Okay, I would suggest now to have another 5-minute break, so we continue at 15:08. If you have questions, I will stop sharing the screen. Raise your hand or put them in the chat. And I will see you back in 5 minutes at 15:08. Okay, welcome back everybody. Yeah, let's start with another poll. As an introduction to cadastre. You should now see two questions again about cadastre or land administration. I mentioned it already quite a number of times in the first part of the lecture today. I hope you read the articles, also checking if you're still there. So first question is, okay, what is not really core of the land administration purposes? Who is involved? What is the situation? Where is it happening? Why? When did it happen? What is not part of the cadastre? What should the cadastre not per se do normally? So difficult question because of the negation. And then the second question is about, okay, this fancy 4D stuff. What is the benefit of having this 4D? That's a cool name. It's implemented very well in tools. It will give you no gaps between parcels. It fits well to the current practice, or there are no overlaps between the parcels. So something you also will not want. Okay, I already have 10 questions, so let's stop the thinking time and reflect on the results. So sorry if you did not manage to enter your question, your response to the questions. Okay, the first thing, what is not part of land administration, core data to manage, to maintain, who, what, where, why, when. The correct was the why. Indeed, this is often not recorded. Just the transaction is recorded, but the who is important. Who was involved, who was buying, who was selling, the what, and the location, the parcel, or also the building. The where is important. Sorry, the what is more the right, means ownership. Or sometimes there are other rights, such as you are allowed to pass this piece of land, or even if you are not the owner, you are allowed to live here, like or use the space for building. So like a long lease. So that's the what. The where is the parcel or the building itself. The why is, okay, why you did it. That's not recorded. And the when is important. So that's the time. And so not is the why. That's not included. And the second question, what would be the benefits of a 4D partition in land administration? And actually the benefits are multiple. Not the benefit is the implementation in tools. There were some answers that it would be implemented. Actually, there are very few tools, databases, GIS systems that support 4D. Also not Postgres or QGIS or any competition, Esri or Oracle. It is a benefit that there are no gaps in space due to the partition nature. It's also true that it should fit the current practice, but actually it is not happening like that. In practice, we hardly even have 3D, let alone 4D geometries in the cadastral registration. And it is true that the big benefit is that there are also no overlaps possible. So I now stop sharing the results and quickly go to sharing my screen and go to the last part of the lecture today. And this is titled 4D cadastre. And special attention will be given to utility networks, so electricity or gas, how these will be registered in the cadastral registration, and how they are registered, and how they could even be better registered. This is joint work with a whole team of researchers, some of them working at TU Delft, some outside, even outside the Netherlands, some working at Cadastre or other cadastral organizations. Let's move forward. I'm not sure if you ever have heard of a cadastre. Perhaps that should have been the first poll. Do you know what a cadastre is? I'll give a quick explanation. Then I will go to a description of the 4D cadastre. Then focus on the specific object type of utilities. So normally people think when cadastre is being discussed about the land parcels, sometimes the apartments or the building rights. But okay, I will focus a little bit on the utilities. Then I will have a look at some other types of objects where also the third dimension and the time, or 4 dimensions together, are relevant. Some reflections before concluding the last part of the lecture today. So this is looking a bit in the who, the what, and the where, and in cadastre or terms, sometimes also called the subject, that is the who and the person, the what, the right, or the and the where, the object. A bit strange names, but these are being used. By the way, if you're interested, next year there will be a course called Geo 1012 that will be about the land administration, and go more into the details, the legal details, but also the system and the technology details. Traditionally, and I think many of you will have seen a cadastral map. They're kind of boring maps. You see on the right hand side a fragment of today's cadastral map in the Netherlands. When you request it over the internet, you get a small map back. It has boundaries of the parcel, it has the buildings on top of them, and it has some numbers, the parcel numbers, and a legend with some more information. In the past, they looked a bit different, even also a bit of coloring applied. Some objects got a different color, like the church was a bit purple, and the buildings were a bit red. And here the buildings have no color. One of the reasons is that the reason why the registration was introduced was because people from French, Napoleon, entered the Netherlands. They actually captured the Netherlands, occupied it, and they wanted money, and they thought, okay, let's set up a good tax system based on property. But some things did not have to pay property, for example, the roads, and the owners of the churches did not have to pay taxes, so they got a different color. So that is the reason. So normally people do not like when you are occupied by a foreign power, but I think we can be very grateful to Napoleon that he occupied the Netherlands. He did many good things, not only the cadastral registration. He also set up the education system and the national address registry. So all houses have a house number and in a street with a street name. Very simple things, but if you don't have it, it's very chaotic. Okay, but the issue is the parcel was and the cadastral maps were flat, two-dimensional, And the world is three-dimensional. Here you see what can happen. I have one parcel here with a building on top of it, but I also have a three-dimensional thing, for example, a sewer system with a connection to the land. And the sewer system is passing many land parcels. So who is owning what? It is owned by the municipality, the sewer system, and the building is that owned by the owner of the land parcel. You can have some really tricky 3D realities, like here in Rotterdam. The Unilever building is built on top of some other nice old buildings. They have the protected monument status, so they were not allowed to be moved. But it was approved that it was allowed to build above them. So how to put this on a 2D map. And also the utilities, the underground pipes and cables, the sewer system. They are really three-dimensional. They are below the surface, below the street, below other properties. And things do change over time. The normal selling, buying, splitting of parcels, building of houses, but sometimes a disaster happens, especially if you are living near the coast and the coastline is eroding, then buildings near the coast can get damaged. So for that, I think we need a 4D cadastre, a warning. This is not a reality. And there is no country in the world that has a 4D cadastre. There is hardly a country that has good 3D registration of the parcels or of buildings, apartment rights. But some countries do have already quite proper 3D parcels. And in addition to that, then they should add the temporal dimension and integrate it with the spatial dimension. And this would, really improve the handling of the dynamics in the land administration. And why is this so nice to integrate into a 4D representation? That is a partition. And there should be, that's what is nice about this 2D map from the beginning. It's a nice partition of space, so that there is no doubt who is owning here and who is owning here or who is owning here, because the parcels are not overlapping and there are no gaps in the map. And so it's a good planar subdivision, and the same would be true if we go for a 3D cadastre. And then we know of every part of the domain who is having the ownership rights or other rights. And the same is important for the temporal dimension. If you sell a parcel, at the same moment, the new owner should be registered. There should be no gap in time, but also no overlap. And because if you would have overlap, then at the same moment in time, there would be two owners of the same thing. That is not the intention. So here a visual attempt, what I try to say in words. So here is the 2D partition. And so partition is a subdivision of the domain, here the 2D domain. You can also do a 3D subdivision. So you get all kinds of volumes to subdivide on the parcels, the 3D parcels. And here is a little bit of a try to illustrate the 4D, but I did go back to 3D. I used 2D space and one dimension for time. So at the bottom there is one parcel, a big parcel. At T0 it stays the same until T1, and then it is splitted into 3 parts. This part, and this part. And then it stays the same again for a while, this part over here, until we arrive at T2, and there's not a split. And at this moment, now we have 4 parcels. Okay, I started with a 2D parcel, so polygon, but actually I have a kind of 3D representation, a polyhedron, for this parcel over time. And the same for the other ones, the successors. And this forms a space-time partition. Okay, I started with 2D at a time, but you can also start with 3D at a time, and then you get, say, 4D hypervolumes. And instead of not polygons or polyhedrons, you get, say, polytopes. Okay, a little bit of UML. In this UML model over here, we have a spatial unit, and a spatial unit is a name for parcel, kind of a generic name. And here you see some specializations. Parcel can be a normal parcel, say length. It can be space in a building, for example, an apartment where you are the owner, and then you own that space, and above there is somebody else owning the space, and below somebody else is owning the space in the different building units. And here you see another specialization, and that is for the networks or the utility networks. So legal spaces for utility networks that should be registered. They're all specializations. So good to see a bit of UML and to think back, okay, what does this arrow mean over here? So this is inheritance. So this is the general class, a special unit. And here is a specialization, a spatial unit specifically for utilities. Here we have something else, and then I stop explaining UML because that was Wilco's task. Here you see an aggregation. So the building units or the apartments are part of the whole building. So that is what is being explained over here. So now utilities. They are a nice candidate for 4D objects because per definition the third dimension is important, and many utility networks are below the surface or sometimes above the surface, and on top of that something else is happening. There is a road or there's a grassland. The current systems do have issues or problems with managing utility networks or the legal spaces of them. And they really do change over time. The networks are extended or sometimes they are sold. In the Netherlands, for example, the internet cables and the television cables are privately owned by companies like Ziggo, for example, and they sell and buy to other companies. In many countries, the utility networks are not registered as cadastral objects, but in the Netherlands, the law says they should be registered as cadastral objects, as real property, which you can own, sell, buy. You can get a mortgage on it to finance it. And they should have their own geometry in 3D. And they change over time, so 4D again. So a little bit of background on Netherlands. It was rather recent. Actually, to the utility registration, there are two sides. There is the technical registration about, okay, where is the actual pipeline and what is the material or the cable, and that needs to be maintained to avoid damage when others are starting to construct and start to dig into the ground. And in addition to this technical registration with the actual pipelines cable information, there's the legal registration that is protecting these spaces needed to have a place for the pipelines and the cables. And you need to own the land or have a right to do something on that land or under that land. In the Dutch Supreme Court in 2003, it was stated by the judges that the underground networks are considered as real estate objects, or should be considered. And after that, also the Dutch civil code was changed and modified, and from that moment onwards, the Netherlands Cadastre was responsible for this registration. However, on the map you do not see so much. You see a little bit like these dotted lines over here, representing on the surface the underground location. Could be much better. Information infrastructure. So I talked about the cadastre, talked about utility networks, and actually you could consider the physical utility network description and topographic information, topographic maps and cadastral maps as part of the information infrastructure. And you can use them together, the different sources. And even more advanced, you could refer from one source to another source. For example, the legal space intended for a utility network could refer to the actual pipeline or the actual cable that is lying there. It's important that you standardize the information content and how to access this. So there's a lot of standardization needed, and also legislation at European level. And there's Inspire that is regulating this, and in the Netherlands we have called the base registrations. They are defined in law, and Bastiaan van Loenen will tell you more in the legal course in the next quarter. But here is an example of a link that is over the information infrastructure, so over the SII. Over here you have the utility network, the segment and the node. These are considered modeling the utility network itself. They are external to the cadastral network. Here we have the cadastral registration again, with the network reserve or the space needed for the utility network. And there is a kind of association. And so we link the legal space to the physical object. And to make it manageable, these are different registrations, but you can access them via the SII, the Spatial Information Infrastructure. Okay, utilities are not the only good candidates for 4D representations. Here an example from another country, from Australia, Queensland. We are now looking at the city of Brisbane, city center. In blue you have a big parcel for the river, the Brisbane River. Okay, little fact, the Brisbane River is supposed to be the oldest river on Earth. I'm not sure how they know it, but it's what they say over there. In orange you see parcels that are related to roads. And in purple you see volumetric 3D parcels. They are a bit further than we in the Netherlands, and they do allow the registration of 3D volumetric parcels. And they also do allow for the apartment buildings to have the 3D geometries for the different apartments. But their cadastral map is looking like this, a 2D map with indication that you have volumetric parcels in purple, or building units in red. And so these are actually stacked on top of each other. You cannot see them in the 2D. Actually, this big, this purple tunnel is going below the normal road and then going below the river, to give you an impression. And look over here at the top. There is this purple thing, and it is intersecting with the land parcels at the Earth's surface. And then it looks like this. And this is a volumetric parcel for the tunnel, for a part of the tunnel. But over here there's a kind of wiggly boundary, and that is because the boundary is defined as the boundary of the river, and the river boundary may change due to erosion and depletion. And that means this object is actually a 4D object. So here you see the 3D, but this boundary is changing over time. And that would make it a 4D hypervolume, actually defined by law and registered as such. Difficult to show, but it's like that. I will skip the next example about a moving river. I will show you this example. This is also true, no imagination, actually the way it is registered. This is a big apartment complex, also in Queensland, near the Gold Coast, which is the nice beach over there. And people use this often for their holidays. But they are owner, and they are not owner of a single apartment forever. No, they are owning a single apartment, say 2 weeks of the year. And that means this apartment, this 3D space, for 2 weeks a year is a time interval, and that is repeating. It can be seen as a real 4D representation. And you can sell it, this right, that you own it, and you can get a mortgage on it, so get a loan to buy it. So this is really a 4D case, true 4D. So this is really the intertwining of the buildings. And this is really nice. So I will now end with a demo. I'm not sure if I should change back to the normal pointer. How do I get my normal pointer? It seems to start like this if I'm having the laser pointer. Well, pointer options here. No, don't want. Normal arrow. Okay, I will do it differently. This is my last slide anyhow. On the nearly last slide, please have a good look at what is told over here. The benefits of 4D and the distinction between the legal space and the physical object. You need legal spaces to be allowed to have a physical object here. It can be a building, apartment, can be a utility network. But they are different things, the physical object and the legal space. This is the advantage of combining space and time. One of the disadvantages is that you integrating is that there are no systems available, no database, no GIS system, no standard. And so it's not state of the art. And if you use separate attributes, that is state of the art. And as you can imagine, dogs in my house. Sorry for that. I will continue. This is the splitting. Full integration has benefits, as shown over here. No gaps, no overlap. That is really one of the benefits. And also you can do things of moving objects. I showed the moving river, but some other real rights are described as moving objects. For example, rights to have your cattle on the land, and the cattle may be moving over time. And that can be also recorded, not in the Netherlands, but in other countries. Okay, now I quickly go to the demo. And you can also follow the link yourself. So go to the browser, go full screen. I have a bookmark of that thing over here. This is the 3D Raster demo. So this is the same link as was in the presentation, and this is a visualization of the 3D parcels in the database. I hope you see the loading of the parcels. The background is imagery of the cesium globe, and you can zoom in, you can rotate, you can even see, if you look by the perspective, that there is this tunnel I was talking about. But cesium has a limitation. I cannot look below the surface. So how to see the tunnel in this perspective, you can imagine it. So we made a trick that we said, okay, we can raise all parcels 200 meters. And now we have moved them upwards. So I'll zoom out a little bit. And if I now rotate, oh, you can see they are above the earth here, but you also see over here, move closer to it, this tunnel below the surface. Here you see all the parcels on the surface. So rotate here. It has nice functionality. Okay, let's go to okay. So this is a normal parcel. I can click on it and I get properties over here. But I can also, not too far, click on an apartment. No. Oh, yeah, now I have the apartment. So you see the highlight of the 3D volume. I get the survey plan and I can get more information. This is now going to the cadastral database to get the query. I can also type in the name of an owner and then retrieve. So let me try the other way around. So if I try Wicklow, or part of the name, Wick, and then search. So apparently Wicklow is owning all the apartments. Also that one. Yeah, that's correct. And so if you know the name of an owner, you can also search the property. Okay, have fun playing with this prototype. It was produced in the master thesis project of Barbara Semmelini, and Marianne de Vries helped in the supervision, also with the development. And so Marianne, who's also helping you with the lab, the GeoDBMS lab. Okay, we are over time, 10 minutes. Time to stop the lecture, unless there are urgent questions. Oh, I see 5 questions in the chat. Okay, quick question. LA is land administration. That's the first question by VM. Question by Theo. Does a natural owner of a parcel, whether the parcel receive any compensation or reimbursement? No, there were no compensations. Before these utilities, you had to tolerate on it, and that meant a restriction to your parcel. You were not allowed to dig there or to build something at that part of your parcel where the utility pipe were crossing. So also main pipes could be on your land. In general, the main connections, the main pipes, are below the government properties, such as the roads. Of course, there are always side connections to the individual buildings and houses. So that did not change. And last question, rather quickly. The Dutch cadastre. I must say, the Dutch cadastre, despite all our research in Delft, is still mainly 2D. There is only one 3D parcel, and that is the parcel you may know. That's the railway station of Delft. That has been used 2 or 3 years ago in an experiment to register as 3D parcel. But it is officially registered as 3D parcel, but it is not visible as such in the cadastral map. So we have a lot of work to do in the Netherlands. Okay, with that, I would really like to conclude this lecture. Thanks for listening. Thanks for hanging on. Have a good weekend. See you next week.